couple students in here did a great job on their quiz just now. Hopefully you did as well. As we move into our next chapter, our new section really of our textbook, and there's 3 sections to our text, right? We've studied trigonometry, we'll study analytic geometry, we'll study calculus just at the very last chapter. But before we get into there, it is February. It is the month of love, of pink and red and stuff, and wore red tie and everything, because on my mind as we start this next chapter, I'm reminded of a love story. So we're going to have story time with Mr. Nadaski. I want to tell you a story about a little boy named Al. Al was a little Hindu boy in India, and didn't have a lot growing up, but as he grew older, he grew to be a very accomplished, very refined young man. But he wasn't fulfilled. He was missing something, right? Well, about the same time Al is growing up in India, there's a little Greek girl named Gia. She also grew up from poor roots, and she studied hard. She grew to be an intelligent young lady, an accomplished young lady, very attractive young lady. Many men sought to get to know her, but she's never really interested in any of those. Both of them on their journey for fulfillment, they traveled to France where lovers meet. And sure enough, in France where lovers meet, they met. This is back in the early 1600s. These 2 young people traveled to France, and they met a mathematician of all people in France. You were wondering where the math connection came in, named René Descartes. And René Descartes introduced these 2 young people, and it was love at first sight. They realized they were meant for each other. They were so indebted to René Descartes for introducing them that they actually asked him to perform the wedding ceremony. Now, you might think this is strange, right? Nowadays, it's ministers and justices of the peace, but on a boat or a ship, the captain can perform the ceremony because he's a man of eminent standing. Back in this day, mathematicians were held in very high regard. The good old days. Well, anyway, René Descartes performed the ceremony, and as they were saying their vows, he said, "Do you, algebra, take geometry to be your wedded wife?" And of course, he said, "I do," and she said, "I do," and he said, "I now pronounce you analytic geometry." That beautiful couple traveled to England. They had a little son there in England named Cal. Well, Calculus is his full name. We call him Cal. And that's the beautiful love story of how algebra, developed by the Hindus in India, geometry, developed by the Greeks, really married, if you will. Those 2 separate, distinct branches of mathematics came together to really form a new branch of mathematics, a higher branch of mathematics, analytic geometry, and it laid the foundation for calculus, which, I mentioned England, Sir Isaac Newton credited with discovering the calculus. But it came as a result of this marriage that René Descartes discovered as he was, we'll give credit to another Frenchman, by the way, Pierre de Fermat also, made some progress there in analytic geometry and recognized we can actually marry these 2 branches of mathematics. So anyway, did you like that love story? Yeah, I came up with it all by myself. All right, there is a little bit of truth in the story. All right, you don't have to write the whole story down, but there are some things that I want you to know about analytic geometry, if you'll write this in your notes. The disgust on Jamie's face when I said, "Do you algebra?" She's like, "Are you kidding me?"
So like that, like there has to be longer names.
Anyway, analytic geometry is really a combination, or if you want to write a marriage, you can write that too. It's a combination of a marriage of algebra, geometry, and trigonometry as well. Algebra, geometry, and trigonometry. Although trigonometry really could be viewed as a subset of geometry, right? I mean, we looked at it last year in geometry, the study of the triangle. It's really not separate from geometry, but another branch, an offshoot of geometry anyway. So, that's why I just said algebra and geometry, but trigonometry, you could lump that in as well. You need to know it laid the foundation for calculus, which is why we have to get through this before we can get to the calculus. So So laid a foundation for calculus. Really, truly, here's your definition if you're looking for it. It's the study of geometric characteristics. It's the study of geometric characteristics of lines, curves, shapes, and here's the key. That all sounds like geometry. And their algebraic equations. It's the study of geometric characteristics of lines, curves, and shapes, and their algebraic equations. We study all kinds of things, angles and line segments and parallelograms and trapezoids and rhombuses and rectangles and triangles and stuff last year, right, in geometry? We're going to put algebraic equations to all of that and put it all on the Cartesian plane in analytic geometry. Two names to note. First one, René Descartes, is one we should remember from, spelled René Descartes. Okay? René Descartes, which we know of him from Algebra 1 when I first introduced the Cartesian plane to you. A lesser known mathematician who still deserves a fair bit of credit, Pierre de Fermat. Not Fermat, but Fermat. Spelled Fermat. Another way to think of analytic geometry is, there's weeping, wailing, gnashing of teeth across the wall from us. Sorry about that. Is the analysis side. Why do we call it analytic geometry? We're analyzing. We're thinking. We're discovering properties that in everything in math is a shortcut, right? How can we do something quicker, faster? And so one of the things we're going to start with here is analyzing equations and deducing truths about them without necessarily having to do graphing first. So there's going to be a graphing emphasis. You're going to use graph paper frequently in this class. But there are some ways in which we can actually analyze situations before we get to the graphing. So the next section in your notes, in the first section of analytic geometry, we want to talk about are three foundational analytic tools. As we look at equations and the shapes that they form, when you take an algebraic equation, we know about some of these already, right? We know about parabolas. We studied those, and we talked about straight lines, linear equations, obviously, in depth, both of those, right? In Algebra 2. Algebra 1, linear equations, not as much with the parabola. I think we just touched the tip of the surface on parabolas. We also looked briefly, remember, at rational functions and the hyperbolas formed by asymptotes. Well, we're going to study three foundational tools that will help us to analyze other shapes as well. The first one is intercepts. Knowing where a curve or a graph or a shape is going to cross axes can help us to kind of get a feel for what it's going to look like without doing a whole lot of extra work on the graphing. This is perhaps the most powerful analytic tool. But another one that's good to know is symmetry. If we know the symmetry of a graph, then that'll also help us to figure what we're doing with that particular equation, what it's going to look like. The last one is actually two things, but I'll make them a combo package for what I think are obvious reasons. That's domain and range. We always refer the two of them together anyway. So the domain and range of an equation. We only have time to preview these in this lesson. In our next lesson, we'll do a lot more practice with them. But let's talk about these three analytic tools. Let's talk first of all about intercepts. Well, as we think about intercepts, of course, we know that's where a graph crosses the axis. So two types of intercepts, right? We have x-intercepts and we have y-intercepts. X-intercept, of course, is where the graph crosses the x-axis. Let's think about this. What is true of every point on the x-axis? Every single point. What's true of it? be like 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, 0, negative 1, 0, negative 2, 0, negative 3, 0. Every point has a y value of 0, right? Because this is the 0 of the y. If every x-intercept point has a y value of 0 and then some x value, right? And think about the y-intercept for a minute. What's true of every single point on the y-axis? Its x value is 0. And of course the y value is just whatever the y-intercept happens to be. Notice intercepts that are characterized by zeros. So how would we discover intercepts? Here's the key. To find an intercept, you're going to plug in 0 for the other letter. What do I mean by the other letter? Well, if you want to know an x-intercept, you plug a 0 in for the y. You want to know a y-intercept, plug a 0 in for the x. And it's going to tell you where the other intercept lies. So intercepts are very easy to calculate. You might even remember back to your Algebra 1, Algebra 2 days and finding intercepts to graph straight lines. Really easy. Plug in a 0, plug in another 0, you're done, right? Intercepts, a very powerful tool in determining what a graph is going to look like, what a shape's going to look like, without having to go to a lot of other trouble. Another tool is symmetry. Now, when we think symmetry, maybe in your own words, what does that mean? Same on both sides. For instance, if you take the human body and you cut it right here, does it look the same above and below? No. But if you cut it right here, but not proposing you actually do this to me or anything, but if you cut right here, the two sides should look roughly the same, right? Maybe not perfectly the same, but roughly the same. You see that symmetry in flowers, butterflies, all kinds of things, right? Symmetry is beautiful. Symmetry is what makes things look good. And so let's picture symmetry here. If a graph is symmetric to the x-axis, then that means that what you see above and below the x-axis should match, right? I would not be symmetric to an x-axis, right? Above and below doesn't match. But if I had something, for instance, like that, for instance. Okay, what we see above, what we see below matches. If we had something like that, what we see above, what we see below matches. If we had, even something as basic as that, what we see above, what we see below matches, right? Basically this, if I take a random x value, there's two y values, but if this is like 3, this would have to be negative 3. If I take this x value, well, I've got this point. Well, if this is like, 8, then this would have to be negative 8, wouldn't it? For a given x, there has to be two y's, one positive, one negative. So that if I were to put a negative in for the y, it wouldn't change anything. Because it already has a positive and a negative. Put a negative in for a y that was negative, it give you a positive, but you have a point there. Plug in a negative for a y that's positive, it gives you a negative, but you already have a point there. Does that make sense? Similarly, if I had y-axis symmetry, well, that would be, for instance, like I explained the human body, right? What you see on both sides of the y-axis is the same. This is your non-shifted parabola that we talked about in Algebra 2. This would be, let's see here. This would be, for instance, we even looked at like the cosine curve, right? Something like that, where it matches on opposite sides, okay? Basically, if you pick a particular y value, you have an x here, you have an x here. Well, if this is 2, this has to be negative 2. Take this particular y value. Point here, point here. Well, if this is, you get the idea? For a given y value, a positive and a negative x have to be present. There's another type of symmetry we could have, and that's origin symmetry. Now, you might be thinking, I remember the last two. We talked about y-axis and origin symmetry before when we talked about even and odd functions back in chapter 5. Vaguely remember that? Well, here we're talking about equations, not necessarily functions. Remember, a curve that looks like that is not a function, right? It doesn't pass the vertical line test. But we're dealing with all equations, not just functions. But origin symmetry, we looked at that as well. We said, for instance, if we had a curve that comes in like that, these two quadrants match each other. These two quadrants match each other. If we had an equation that, let's go through the origin here. If we go back up through the origin, something like that. These two quadrants match. These two quadrants match. That'd be origin symmetry. Even if we had a rather familiar looking shape like this. These quadrants match. These quadrants match. Now also, by the way, notice above and below match and side by side match. So a perfect circle centered at the origin, right, would have all three types of symmetry. So it's possible a curve can have all different kinds of symmetry. But the idea with symmetry is where something's positive, for instance, if x and y are both positive here, they're both negative here. If x is positive and y is negative, then x is negative and y is positive. They're always opposites in pairs. Change the one, you also would have to change the other sign to show the symmetry. So you get the idea, the positive negative is kind of the prevailing idea with symmetry. Here's our keys. To determine x-axis symmetry, you have to plug in a negative for the y value. And if you did, it would give you something that's still on the graph. Y-axis symmetry. You'd plug in a negative for the x, and it would still give you value on the graph. The origin symmetry, because if one changes, the other has to change with it, we're going to plug in negative for both x and y. But as we plug in negatives, what are we looking for? Well, if it's got that symmetry, then plugging in a negative isn't going to actually change the equation at all. So the question you're asking yourself as you plug in these negatives is, can I plug in a negative without messing up the equation? Can I plug in a negative without messing up the equation? And I'll show you what I mean by that here in just a moment. The last analytic tool, as I already mentioned, is domain and range. Let's talk about domain. You might recall we said domain is all the possible values you can plug into a function. Well, we're not talking about functions. So these are all the possible x values that are in the graph. All the possible x values that are in a graph. Range used to refer to all the f of x values we'd get out of a function. Well, in this case, it's not a function, but this still refers to all the y values in a graph. Knowing the domain and range tells me how far side to side a graph will go, how high up and down that a graph can go. Knowing all three of these things, the intercepts, where it's going to cross the axes, the symmetry, where there's going to be mirror images, if you will, and how high and how low, how far to the sides a graph can go, can really give me a very accurate picture of what a graph is going to look like. How do we determine domain and range? Well, the key to determining domain and range is kind of a general thing. You want to set the equation equal to the other letter. Again, what do we mean by that? Well, if you're trying to find the domain, which is your x values, set the equation equal to y. If you're trying to find the range, which is all possible y values, set the equation equal to x and try to see, are there any limits on the letter you're actually looking for? So if I'm trying to find the domain, set it equal to y, and then look at the x and say, are there any limits on my x? We talked about a lot of limits back in Algebra 2. We're just going to look at three primary limits in this course. First of all, you're not going to see this often, but trig functions, we're not completely done with trig. There's a little bit of a marriage of trig in here. Are there any trig functions? Because trig functions have inherent limits to them, particularly sine and cosine, for instance. you can't get anything above 1, right? Or below -1. There are certain values where there's asymptotes in other functions. So trig functions, we won't see those often though. If you have fractions, remember that a denominator can't equal 0. So you may have a hole in the graph or an asymptote in the graph if there would be a denominator of 0. Another one that you'll see is if you have a square root, your radicand has to be positive or between 0 and infinity. If you have a square root, your radicand has to be between 0 and infinity. So any value in there that would cause you to fall outside that realm of positive radicands is off limits. It's limited out of the domain or the range. Let's look at an example here. Write this in your notes if you would. X squared plus 3y is equal to 6. Let's make that a 36. I can't read my own writing. Let's go with an x squared plus 3y equals 36. As we analyze this equation, discover what it's going to look like, let's start by analyzing our intercepts. The key to intercepts, remember, is to plug in a 0 for the other letter. So if I want to find the x-intercept, I'm going to plug a 0 where it says y. Well, if I put a 0 right here, this whole term becomes, and it just drops off. I'm left with x squared equals 36. What is x? Positive and negative 6. I actually have 2 x-intercepts. The y-intercept, remember, you're going to plug a 0 for the other letter. We're going to plug it in for the y. Well, again, or the x rather. You plug a 0 in here, this whole term disappears. What's your y? 12. So 0, 12 is your y-intercept. Let's determine whether or not we have symmetry in this. To determine whether or not the graph is going to be symmetric above and below the x-axis, stay with me, we're going to plug a negative in for the y. Well, if I put a negative right here, it says x squared plus 3 times negative y equals 36. What's 3 times negative y? Did my plugging in a negative mess up the equation? Did it change? Did it change? It did. So plugging in a negative didn't work. I do not have x-axis symmetry. To determine whether or not we might be symmetric side by side across the y-axis, we would try to plug in a negative for the x. So let's try plugging a negative in for the x. Get a negative x squared plus 3y equals 36. What do I get when I square a negative x? Did I mess up the equation at all? No, it's perfectly intact. This particular graph is going to be symmetric side by side across the y-axis. For origin symmetry, we would have to plug a negative in for both of these. But again, what's 3 times negative y? And this, when you square it, is still a positive x squared. This becomes a negative 3y. Did I mess up the equation? Yeah, so it's not going to be symmetric to the origin because I couldn't plug in negatives for both of them. Domain and range very quickly as we finish. We take our equation, x squared plus 3y equals 36, and to determine the domain, which is all possible x values, I want to set the equation equal to the other letter y. To set it equal to y, I'm going to subtract away the x squared and divide away the 3. Is there anything that I can't plug in for x? Are there any trig functions? Would plugging certain things in for x cause me to have a 0 denominator? No, that's always going to be 3. Are there any square roots that I could possibly end up with a negative? No. There's no limits. My domain is all real numbers. That means my graph goes to infinity and negative infinity outward, side to side. Let's determine the range. Range is all possible y values. So I'm going to set the equation equal to x, the other letter. Now to set equal to x, I'm going to subtract away the 3y to get x squared, and then take the square root. Are there any limitations, any limiting factors here that would keep me from being able to plug whatever I want? Is there a number that if I plugged it in for y would mess things up? 12 is fine, but 13 would be a problem, wouldn't it? 14, 15, 16. What about negatives? Can I plug in negatives? Negatives are great because they offset, make it even more positive. But I can't plug in anything bigger than 12. I can go down to negative infinity on my graph, but the graph is never going to rise higher than a 12. My range is negative infinity to 12. I can tell then what I must be looking at with intercepts at 6 and negative 6 on the x-axis, and intercept of 12 on the y-axis. Mirror image side by side, constantly spreading outward, but only going downward. I must be looking at this parabola. All from that analysis. That's the kind of thing we're going to be working on in future lessons. All right, no homework this evening. Have a wonderful rest of your day, and you are dismissed.